Welcome you all. In this lecture, we will discuss about the single layer ANN with non-linear activation function. In the last video, I have discussed about the different activation functions along with the our what is the neuron and its architectures. So, for the better simplicity, I am taking single neuron with only one input. That is, we can call it as X. Okay, and this output is Z. Then followed by activation function. I am taking sigmoid function. Okay, then output we are considering that is y cap. Okay, this is the estimated output. This is the output obtained from the inputs, and there is a weight and one more bias also we are considering. Okay, so here x value is the, we can take that as a x value is 1 and 2, and w is the fix, we can get make it fixed, that is 0.5, and bias is we can make it 0.1. Okay, then expected output, what are the outputs we are going to expect means that is 0.5 and 0.8. So here if I am giving a input 1, my expected output should be a 0.5. If I am giving a input 2, my expected output is 0.8. So accordingly we have to decide the W and beta by using nonlinear optimization. Okay, so let us start the operation. So before going to this one, all of you know, then this Z we can represent like this: Z equal to XW plus B. So here I am not considering x1 and x2, only for the better simplicity I am taking only single input. Okay, so what is x is the, x is 1 and w is the 0.5 plus zero point 0.1. It will give total 0.6, right? So next one is the, I am substituting this one, that z in sigmoid activation function. So that is y cap is equal to f of z, that is equal to 1 by 1 plus e to the power of minus z, right? That is 1 by 1 plus e to the power of minus 0.6. It will give you the value of, already I have calculated, so 0.645, right? So this is the predicted output. We can call it as a, this predicted, that is y cap. Actual y is the 0.5 and predicted it is obtained 0.645. So therefore we need to find the what is the loss. Actually we are not exactly obtained the 0.5, somewhat deviated from its output. So what is the, how much the difference is? So that we can write that it is loss function. Let us represent by L. Okay, so here loss function is can be taken the mean square error or mean absolute error. So here I am taking mean square error 1 by n summation of y cap minus yi whole square. So only two samples were there. So therefore 1 by 2 for this one, our predicted output is a 0.645 and actual output we need, that is 0.5, right? Whole square. So this will give you approximately 0.0105. So this much loss is there. So we need to reduce this loss. If loss is getting 0, then we are accurately reaching towards the expected output. So how we need to estimate, how to change this, how to reduce this loss. Okay, that is our target. So what are the opportunities to reduce this loss means how we can reduce, because we cannot change the input, that is input is fixed to the one, and the only possibilities are one is a W and one is the B. By changing these weights and bias, we can change the step, that is predicted output, which is close to the our y, right? So here, therefore, first week if I am taking w, that is a weight, dou L by dou W. So if I am differentiating with respect to W, we will get the result. But the problem is here, if I am taking, there is no W in the loss function. So if I am differentiating with respect to W, then it starts giving 0. So that's why we need to modify our differentiation, that is a loss function, updates or updated function, to the form of like this, dou L by dou y cap, then dou y cap by dou z, dou z by dou W. See here, now in loss function, dou L by dou y naught means we can demonstrate with respect to y cap. So we will not getting any 0, we will get some solution. At the same time, one more, in y cap, that is there is a z. So if I'm differentiating with respect to z, I will get some solution. And one more, dou z by dou W. So W is the, if I am W differentiation of z with respect to W, we will get one solution, right? So by the way, if I'm cancel this one like this example, so if you check this and this one and this one will cancel. Again, we will receive dou L by dou W. So the our right hand and left hand is matched. Now let us start the one by one. What is dou L by dou y naught? If I'm differentiating this one, that is L equal to half into y cap minus y whole square. What is the differentiation? Is simply y cap minus y. Okay. Next one is y with respect to this one. If I am differentiating with respect to z, that is dou z, the function directly I am writing, it is sigmoid function f of z multiplied with 1 minus f of z. This is the differentiation of the sigmoid function. And last one is a dou z by dou W. And this one, if I am making differentiate with respect to omega, what will happen? Sorry, W. Then simply it is x, because W is 1 and B is 0. Now substitute these values. What is a y cap? Y cap, what we have obtained, that is 0.645. Okay, 0.645. What is the y expected output? 0.5. What is fz? Fz is again 0.645 and 1 minus 0.645. And what is the x? X is the, we know that x is 1, right? So x is multiplied with the 1. So this answer I am directly writing 0.0332, right? This is the dou L by dou W. But as of we know, that is updating the new weights. What is the formula? According to the gradient descent algorithm, it is W new is equal to W old minus alpha into dou L by dou W. So here till now we have not taken what is alpha. Alpha equal to latest learning rate 0.1. What is the W old? That is this one is the, okay. This one become W old, right? So W old I am writing over here, that is 0.5. So now 0.5 minus 0.1 and this answer, okay, 0.0332, right? If you are finding this one, it will give you the answer 0.497, right? So this will the W new value. Next one is the one more parameter we need to optimize, that is B. Okay. One W we have optimized and we obtained the results 0.497. And another is a bias term for optimization. Write down dou L by dou B, same dou L by dou Y cap, dou Y cap by dou Z, dou Z by dou B. So dou L by dou Y cap is a no more changes, Y cap minus Y. And here also sigmoid function no more changes, 1 minus f of Z. And dou Z by dou B is the, now it become 1, because if you are respecting, this is Z is the xw plus B. If you are differentiating with respect to B, you will get multiplied with 1. So if I am substituting this one, how it will come? It is the, again, same answer, because no more changes. Here itself also x equal to 1 and here b equal to 1. So this will give you again the same answers, 0.0332. Right? Now if I want to update the new, that is b new, b old minus alpha into dou L by dou B. So B new is the, B old is the, we know that is 0.1, right? So therefore 0.1 minus alpha is a 0.1 multiplied with 0.0332. So this will give you 0.097. So new, W new and B new we have obtained after optimization. Again I am drawing this diagram, that is now B is equal to 0.097 and W equal to 0.49. How much we got it? 497. 497. Now X and again Z, then after activation function, then finally your Y cap. Now first sample has been completed and another input is there for X equal to 2 and expected output is the 0.8. So X equal to 2, now change it to X equal to 2 and your expected output is the 0.8. Now same we have to execute. After optimization, let us check whether we are getting the perfect output or not. So again Z equal to xw plus B. So here xw means x is the 2 multiplied with 0.497 plus 0.097. So this will give you, the answer is 1.091. Okay. After substituting, again we have to find the y cap equal to f of z, that is 1 by 1 plus e to the power of minus z is equal to 1 by 1 plus e to the power of minus 1.091 will give you approximately 0.748. So now we need to find the loss functions, that is loss how much? Half into y cap minus y whole square. It is half into 0.748 minus what is actual? This one is a, we have to get the expected output we have to. So this will give you 0.00135. This much difference is their loss. Again we have to reduce this loss because we have not received closely 0. So for reducing this loss, again we need to use the gradient descent to optimize the both parameters, both W and B. So that by using back propagation algorithm is called as a back propagation algorithm. So dou L by dou W equal to dou L by dou Y cap and dou Y cap by dou Z, dou Z by dou W. So this will give you, it is a Y cap minus Y, Y cap minus Y, again f of Z, 1 minus f of Z And if you are differentiating, that is your z equal to xw plus b. Here itself again same x. Okay. Then if you made your calculations, finally you will get approximately, now it's x equal to 2 and f of z is your 0.748 and y cap is the again 0.748 and y is the zero point 0.8. So after substituting all these terms, you will get 0.188, right? And the next another of this one, if I'm optimizing, that is w new. What is w old? W old is now, right now it is simply w old is a 0.497. Remember, it is not a 0.5. 0.5 already updated to the 0.497. Now this become a w old. So 0.497 minus alpha zero point 0.1 into this one 0.188. Okay, this will give you 0.499, right? Next one is a dou L by dou B. So this dou L by dou y naught y cap, dou y cap by dou z, dou z by dou B. So again dou B means it will dou z by dou B will come because z equal to xw plus B means it is always will come 1. So this will give you minus 0.0098. So this, if I am substituting in the B new, okay, substitute in the B new, B old minus alpha into dou L by dou B. So what is B old? B old is the 0.097 minus 0.1 minus 0.0098. Okay, this will give you 0.098. So now again, this will, what is a W new is the 0.499 and B new is the 0.098. Okay. So this way, every iteration, this is complete one epoch because now both two, this X is the two inputs we have completed with updated weights. So this one we can call as a one epoch completed. So this process will repeat several times to optimize this loss approximately equal to 0. The first epoch and second, third iteration, fourth, fifth, like this. This the error is getting reduces. These weights are continuously updated, and after this one finding the loss and loss will, whether it is 0 or not. If it is not 0, again weight and bias will be updated. This process will continue further and further to reduce the loss. So this is the way of uh, finding the optimization using nonlinear activation functions. Okay, so here this is called as a back propagation algorithm. Okay, now in the earlier video only that is feed forward. This is, if I'm going in this way, this is only feed forward. So after taking the output, we are modifying our weights. So this is, we giving a feedback. It is indirectly we can say that by using the feedback we are optimizing weight and bias. So therefore it is called as a, also called as a back propagation mechanism or algorithm, you can say, right? So this by this way, every whatever the problem they have given in the example, and this is for the, okay, this is for the one input. If I am going for the multiple inputs, like example, there is a x1, x2 and x1, w1, w2, and we have a b, then z, then activation function is a sigmoid, then y cap. Then in this case, what we have to do? So in this case, no need to worry, just dou L by, because now weights individually we have to update. In the earlier case, only one weight, that's why I have taken W new, but here two weights are independent weights were there. So therefore, dou L by dou W1 is equal to dou L by dou y cap by dou z by dou W1. With respect to W1, we are differentiating. And another one is a dou L by dou W2 is equal to dou L by dou y cap by dou z by dou W2. It's another weight. And bias is the common. Only one bias. Therefore, dou L by dou y cap by dou z and dou z by dou b. So these time three activation form. These are three times we have to do. We have to differentiate with respect to W1, W2 and B, and we need to find the new weights W1, W2 and B. So this is the way to find the optimization in neural network for single layer. Okay, here there is no hidden layers, only single one input and one output. Okay, thank you. If you like the video, please click on the like button. Thank you.